Visualizing a function usually means plotting a graph. For each point, we record an input and the corresponding output under the function f. But what if both input and output are complex numbers? As said in the previous video, a complex number is represented with a complex plane, a two-dimensional object. So both the input and output are two-dimensional, which means we actually need 4 dimensions to properly graph it. We live in a 3D world, so how do we visualize a complex function then? There are, actually, at least 5 ways of doing it. Of course, different methods have their own pros and cons, but I want you to leave a comment on which is your favorite. In this video, I'm going to briefly explain what these methods really are, then use some examples to illustrate how they are used to visualize complex functions. First, let's see what is domain coloring. For this method, we basically treat the complex plane as a canvas for us to paint a picture. For a complex function, each point on the complex plane is the input, and we need to find a way to represent the output. Let's say 1 plus I is mapped to 3 minus 4i. Then at the position 1 plus I, we color it with a color that represents 3 minus 4i. The question is, what should be the color? Well, we can refer to a color wheel. With the appropriate real and imaginary axes drawn and rescaling, 3 minus 4i is here, which corresponds to a bright pink color, so we should color this point bright pink as well. Then repeat this for all the other points and we are done. But what was that color wheel in the first place? The first thing to note is the hue. From red to green to blue, then back to red again. Because of the periodicity, this naturally corresponds to the argument of the output, and the modulus is represented by another attribute of color, in this case the lightness. Basically, in the middle, the color is black because there is 0 lightness, and as the modulus increases, it becomes whiter and whiter. This is convenient because a black spot is precisely where the function is 0, and the white spots are where the function is shooting off to infinity. For example, in this domain coloring plot, can you find out the zeros of the function? Well, the black spots are here. What about the places where the function blows up? Well, the white spots are here. So if you are particularly interested in zeros and infinities, then it is a nice way of visualization. By the way, this particular black spot is quite different from the other two. Can you figure out visually what is the difference? And could you explain this difference if the function is given like this? Don't worry if you don't know the answers, it is completely optional, but if you do, leave a comment down below. The second way would be 3D plots. For any complex function having its input and output, originally we would want to plot points like these. The first two represents the input, x plus iy, and the last two represents the output, u plus iv. But we are 3D creatures, so we need to sacrifice one coordinate and plot these points instead. The missing coordinate, in this case the imaginary part of the output, is represented by the color. For this reason, let's call the resulting plot the re-im plot. For instance, this is the re-im plot of the exact function we have seen before. These two spots are where the function shoots off to infinity, but the zeros of the function are not as obvious. Even if we rotate the surface a little bit, it is not immediately obvious where the zeros are. But let's take a step back. Why do we have to sacrifice the imaginary part in particular? We could have colored the real part instead, making it the im-re plot. We can also instead keep the modulus of the output, and the argument is represented by color. If we do this, we can call it the mod arg plot. If we do the mod arc plot of the same function, we get this. Again, the infinities are quite obvious, but this time the zeros are a bit more obvious as the lowest possible points of the plot, which is somewhat close to the feature of domain coloring. However, the previous reim plot isn't completely useless. As I said in the introductory video, both real and imaginary parts of a nice complex function satisfies an important differential equation, and we call such a function harmonic. And so the reim plot visualizes the contours of a harmonic function, which is still important. Alright, we get onto the third method, vector fields. The rationale is similar to domain coloring. Again, we have a complex function with its input and output, but this time instead of colors, we use vectors to denote the output. Let's reuse the example where 1 plus I is mapped to 3 minus 4i. The point at the position 1 plus I should be attached with a vector corresponding to 3 minus 4i. However, unlike domain coloring, we can't do this to all the other points. If we do, this is the result. You can't see anything. Instead, we only consider a small number of points on regular intervals. But, well, some vectors are way too long to clutter up the plot, so we need to standardize the size, and the missing information about the length can be represented as color in this more refined vector plot. A slight variant is obtained when we consider this as a velocity field, so a particle would follow a trajectory whose instantaneous velocity is dictated by the vector plot. If we do that to a lot of particles, the result is this, a stream plot. This can be made more dynamic by particle animations, but what's more interesting is the polar vector field. Instead of plotting f of z directly, we plot its conjugate. Why? The resulting flow is physical. More specifically, it represents an inviscid incompressible irrotational flow. Mathematically, for nice complex functions, the divergence and curl of the polar vector field is 0, but we will talk about it much later on in the video series. For now, let's go to the fourth visualization method. This ZW plane method is exactly the same as the transformation I've talked about in the Jacobian video. Let's say again 1 plus I is mapped to 3 minus 4i, so the point at a position 1 plus I under f would need to move to 3 minus 4i. Since usually we denote z as the input and w as the output of a complex function, the input is called the z-plane, output the w-plane. Let's see what the squaring function looks like. We first construct the z-plane with these grid lines, and here we go. The result is the w-plane. The most noticeable feature of this method of visualization is that these angles and intersections are still right angles. The only exception is this: the angle doubles to 180 degrees. This is not a coincidence, but again, the explanation is going to have to wait. However, you might have a question. The z-plane is always going to be the grids, so why bother? We can simply draw the w-plane. You might expect my response to be that the transformation animation was great, which it is, but that's not it. I could have chosen any transformation, just that in this case, the most natural transformation is to let the exponent go smoothly from 1 to 2. But that's not the only choice. This is another choice of transformation that is also quite smooth. My point is, that's right, only the resulting w-plane is important. But the z-plane is important in the following way if we don't use the whole complex plane. For instance, what happens to a circle if we apply this function instead? By the way, this function is called the Joukowsky transform. Can you guess what the image of the circle would be? Just guess. Let's see the answer. In case you haven't noticed, this looks like an airfoil. The result is called Zhukovsky airfoil. Historically, this is a good tool to understand the aerodynamics around an airfoil because airflow around a circle is relatively easy, while directly studying the flow around the airfoil is much harder. More specifically, given a circle, the potential flow around it is a standard problem in fluid dynamics, and we can apply the Zhukovsky transform to find the fluid flow around the airfoil, which is a complicated shape. That's probably too much of a tangent, but my point is that Z and W planes are both useful when we want to see the image of a subset of a plane, and we get to the final way of visualization. This method is very similar to the previous one. We have the input sphere, the Z sphere, and the W sphere being the output under the function f. Essentially, a point on the sphere, somehow representing a complex number z, is mapped to f of z, represented by another point on the sphere. The only thing we need to know now is how complex numbers are represented on the sphere. In that 3D space, we consider the xy plane as the complex plane, and the sphere is actually a unit sphere centered at the origin. Now consider the top point as the light source shining onto the complex plane, so this point on the sphere would cast a shadow on the complex plane. That shadow point is the corresponding complex number. However, calling it a shadow isn't entirely accurate because a point in the southern hemisphere wouldn't really cast a shadow on a plane, rather the reverse. What I mean is that a point on a plane casts a shadow on the sphere instead, but still, that point on the plane is the corresponding complex number. That means, basically we can identify the entire complex plane with the sphere, but without that light source, because that light source wouldn't cast a shadow. With that, let's take a look at how the squaring function looks like. Again, you might be able to notice that the angles are right angles, but it might be less obvious that near the South Pole, the angles double. And you might also realize that the South Pole corresponds to 0 as a complex number. Remember that for the same function, in the ZW plane example, the angles at 0 also double. So in terms of angles, these two methods are very similar. However, in fact, angles at the North Pole also double. It's just that this point doesn't correspond to any complex number. But it's a little troublesome to always exclude the North Pole, so we correspond this point to something called infinity, and we can do arithmetic with it in a very precise sense, but that will have to wait until we talk about Möbius maps. So out of the 5 methods, which one do you like the most? Let me know in the comments. Before you go, I just want to say that these animations do take a huge amount of time and effort, so if you want to and can afford to, please consider supporting on Patreon, where you will see the video at least 24 hours before it goes public. The next video will continue complex function visualization, tackling specific common functions and finding some possible problems with them. In any case, if you are new here, consider subscribing with notifications on, liking the video, and of course, do comment and share the video as well. See you next time!